Okay, YouTube, in this video we're going to look at algebraic methods for solving systems, of which primarily we have two. So these two methods are referred to as the substitution method and the elimination method. But recall that our goal here is when given an equation, a system of equations and two variables here with two equations, we want to find a common x and y that when we plug it back into both of these equations satisfies them all. So this first method we're going to investigate in this video is referred to as the substitution method because that's precisely what we will be doing, is using substitution. So step number one, I'll take you right through the steps that I've listed here, but as always it's solve one of the equations for one of its variables. Now, if I said, well, I've got two equations and two variables, so technically there are four variables that I could solve for. Basically, when you say solve for the variable, it means get it by itself. So of all of these variables right here, I want to consider the fact that it would probably be the easiest to get this x in the first variable by itself because, well, it has a coefficient of 1 and it's already positive. Every one of these other ones, we would have to boot the other variable over and then do some division, which is going to cause us to have some fractions. So the first thing I want to mention here is this: which of the variables in the system was easiest to solve for and why? It's going to be x in the first equation, first EQ. And for the reasons why we just stated, it's going to be really easy to isolate that. So I'm going to do this over here. We say x minus 2y is equal to negative 4. Now, here's the thing. Showing my work, I could say, well, adding 2y to both sides, we isolate the x and we get x is equal to 2y minus 4. Okay? I'll put a box around this. I'm going to refer to this as a revised equation because it's really the same equation, but it's been manipulated. The thing I do want to mention though is this: because we solve so many linear equations, it's really just kind of easy to see that really what we did is we just displaced the negative 2y to the right side and it became positive. So now using this revised equation, we actually know what x equals now. We say x equals this in terms of y. The nice thing about that is because what we're going to do with this value here is substitute that expression that we just found from step 1 into the other equation and solve for the other variable. That is to say, we know what x is, and so since I know what x is, I can go to the second equation over here, and instead of writing that x in there, we could say 2 times x minus 3y is certainly negative 6. Since the x and y that we're looking for is actually supposed to satisfy both equations, then I can say, well, since it's the same in the second equation, we can just go ahead and instead of writing x, we could write 2y minus 4. Because they're the same anyways. So we say 2y minus 4, and this is what we refer to as our substitution. But the nice thing about the substitution is whenever you make this substitution, you'll always end up with one variable type. So now we can actually go through and solve this equation. We're going to start by simplifying first. So I would get this here. We would say 4y minus 8 minus 3y is 6. Now combining like terms, putting the y's together, I'd see that I get a single y minus 8 is equal to negative 6, and if we add now 8 to both sides of this equation, we have isolated the y. So I'm going to say y is equal to 2. Now I want to box this. It's really important that you put a box around that. But I'm also going to say this. It just basically means that the point of intersection of these two graphs, if we were to go graph their solutions, the y value that they collide at has to be 2. So now, asking this question, we say, well, how am I going to find the value of x if I know what y is? Well, just like when I knew what x was, I could go substitute that into the equation and find y. Now that I know y, I could plug this back into the equation to go find x, and you hear me say the equation. I really should say any equation in the system, because what I know is, recall that this point is the solution to every equation in the system. So it wouldn't matter if I plugged it back into the first equation or plugged it back into the second equation, but basically step 3 is always substitute the value from step 2 back into the equation, and I say the equation because I'm always going to suggest you use the revised equation. The revised equation was no more than the first equation that we just kind of rearranged, and the reason why I'm suggesting the revised equation is because, well, what is it that we're looking for now? X. X is already by itself in this equation. So substituting now, again, another substitution, this value of 2 back into its equation, we get x is equal to 2 times 2, which is 4 minus 4, so x would be equal to 0. So I'm going to box this, and I also want to write this right here. So our solution to the system is this 0, 2. So if we were to go graph both of these lines, we would see that that is clearly their point of intersection, and they only intersect one time, okay? And last but not least, it is appropriate to check your solution values back in the system, the original equations. So if I plug in 0, 2, This makes this a little bit easier because if I'm plugging 0 in for the x values, they're going to drop out. And if I were to put in 2 into the first equation for the y value, I get negative 2 times positive 2 is negative 4. And that's certainly true. And if I plug in 2 into the second equation, I get negative 3 times a positive 2 is negative 6. So this is our solution to the system.